Hi everybody. Today I'm going to be walking through a proof of the Pythagorean Theorem. Before we jump into the proof, it's just helpful to remind ourselves of some of the scaling properties of area because we're going to actually need this for the proof. So, scaling properties of area. Okay. Alright, so you may remember, right? Let's say we've got a 1 by 1 square. Okay, 1 unit, and the area of that is 1 unit squared. Okay, and let's say that we scale that up by a factor of 3. Okay, so this is a similar square. It's now 3 units by 3 units. And what's the area? Well, it's 3 times 3 units squared, so it's 9 units squared. Okay? So you look at the side ratio, the side length ratio. Let's say the length ratio. It's 1 to 3. Okay? Or another way you could think of it is the scale factor, right? The scale factor is 3, okay, for the lengths. Now, what's the scale factor for the area? Well, the area ratio, the area scale factor, is 1 to 9, okay? Because 9 is 3 times 3, 3 squared, right? Because both of these sides participated in the multiplication to give us the 9, okay? So, in general, okay, if the length ratio of two similar shapes is R to S, okay, then the area ratio is going to be R squared to S squared. Okay, so how does this apply here? Well, R was 1. 1 squared is just 1. Okay, S was 3. 3 squared is just 9. Okay, so you scale by the second power when it comes to area. All right, so now that we've got that under our belts, let's prove the Pythagorean theorem. So remember, the Pythagorean theorem, okay, states that if you have a right triangle with hypotenuse C and legs A and B, okay, then A squared plus B squared equals C squared. Okay. All right. How do we prove that? Well, we're going to start by just drawing a triangle. Okay, so let's start the proof. We're going to start by just drawing a triangle that has legs A and B and a hypotenuse C. Okay. All right. Once we've started with that, what we're going to do is we're going to add to this diagram. So we're going to draw a box around this. Okay. It has the same dimensions so that we've got two right triangles that share a hypotenuse. And then we're going to take this point and we're going to draw a perpendicular, okay, a line segment at a right angle through the hypotenuse C. Okay. Now, this right triangle, the original right triangle, has some angles, okay? And because this angle here is a 90-degree angle, by the triangle sum theorem, right, these two angles have to add up to 90 degrees. Okay, so that means they're complementary, right? So the angle down here is complementary to the angle up here. They add up to 90 degrees. What does that mean for us? That means that this angle up here has to also be the complement of this angle over here, right? Which is equal to this. So you could also figure this out by saying that, hey, this whole thing is a rectangle. These two sides are parallel. These guys are alternate interior angles. And what does this angle have to be over here? Well, you guessed it, same logic. Has to be equal to this angle up here. Again, alternate interior angles gives you that. All right. So what can we tell? Well, we know then that all three of these right triangles are similar by angle-angle similarity, okay? This triangle has two angles in common with this big triangle and so on. And also these two triangles are congruent. Yeah. All right. So given that, let's come up with variables for the areas of these guys. Okay, so we'll call the area of this triangle down here, call that area A. Okay. This triangle over here with the B side as its hypotenuse, we'll call that area capital B. And then this big triangle over here with C as its hypotenuse, we'll call that area capital C. This is also equal to the area of the original right triangle that we drew. Okay. Now, because these two triangles are congruent, okay, the ones that split the rectangle in half, we can write down an equation immediately. It says, hey, A plus B equals C. And we're talking capital letters here. So these guys are areas. Okay. So these are all areas. All right. The amount of space in the yellow triangle plus the amount of space in the green triangle equals the amount of space in the red triangle. Pretty simple. Okay, and then the next thing we're going to do, we're going to use the fact that we proved over here. Okay, so if the length ratio is r to s, then the area ratio is r squared to s squared. Okay, so let's look at the length ratios of these three triangles. Okay, we'll start with the yellow triangle. We'll just look at the hypotenuse. So what's the hypotenuse of the yellow triangle? Well, it's A. Okay, so A. So we're just looking at the length ratio right now. Okay, and then what's the length of the hypotenuse of the green triangle? Well, that's just B, lowercase b. And finally, the length of the hypotenuse of the C triangle, well, that's just C, lowercase c. Okay, that means that the area ratios relative areas are in the ratios a squared to b squared to c squared. Okay. Or another way you could think about it, another way we could write this equation is that a squared over capital A equals, remember, capital A is just the area of the yellow triangle, okay? So this is the ratio of the yellow triangle to the square of one of its sides, okay? Is equal to little b squared. Remember, these two sides are corresponding in the similarity relationship, the a and the b. So little b squared over capital B is equal to little a squared over capital A. And then little c squared over capital C is also equal to both of those. Okay, so all these ratios are equal. Cool. So let's use this relationship as we manipulate this area equation. So we're going to combine our knowledge here. So on both sides, we're going to multiply by c squared over capital C. Okay, so we end up with, first things first, what happens over here? Well, the capital C's cancel. And so we're left with just little c squared on both sides. Okay, sorry, on the right side. And then on the left side, we've got, well, we need to take this and distribute it. So it's little c squared over capital C times capital A plus little c squared over capital C times capital B. All right. And now we're going to use the fact that little c squared over capital C is equal to both a squared over a and b squared over b. So a squared over capital A times A plus b squared over capital B times B is equal to little c squared, just bringing down from up here, okay? So all I did was I replaced c squared over c with the thing that it's equal to in two different situations. So it's equal to a squared over a, so I replaced it with that here, and it's also equal to b squared over b, so I replaced it with that here. Now what happens? Well, the a in the denominator and the numerator cancel out, and the capital B in the denominator and the numerator over here cancel out. And so we're left with just a squared plus b squared is equal to c squared. QED, mic drop, draw your favorite proof symbol at the end. This completes the proof. Okay, so what did we actually do? Well, okay, so we started just by drawing a triangle with sides A, B, and C. We drew an exact copy of that triangle, rotated, so that it forms a rectangle. Okay, we split each triangle, we split one of the triangles into two separate areas proportional to A and B. Okay, and then we saw that capital A plus capital B has to equal capital C because these two triangles are congruent. Then we used similarity relationships to show that the areas had to be in a certain ratio. Okay, that allowed us to write down this handy-dandy equation. And then we used some algebra to show that when you combine the two equations together, you end up with the renowned Pythagorean equation, a squared plus b squared equals c squared. There you go. That is the proof of the Pythagorean theorem.